Yes, ma'am, you are visible.
No, PPT is not visible, ma'am, till now. ओके ओके मैम ओके।
सर वो बोल रहे थे सर एनटीएससी वाला जो ये था इलेक्ट्रॉन क्विज था, तो वो कल
Ashish
जाने
sir,
वाला
you mute your mic.
है।
Madam, in the share button, in the screen, you could get a share button.
डाउन साइड।
किसका शेयर हुआ है? शेयर हो रहा है तो शेयर हो रहा है तो
मैम ये शेयरिंग हो रहा है आपका, लेकिन वो जूम लिंक वाला।
नहीं, आपका जो जूम लिंक है ना मैडम, वो जूम लिंक मतलब आपका जो विंडो खुला हुआ है वो शेयर हो रहा है। तो आप पीपीटी को जाके खोलिए, पीपीटी को खोलने से पीपीटी दिखेगा।
पीपीटी का कौन सा है?
तो वही एक मीटर आपके साथ में चाहिए तो हाँ आप लोगों की तरफ से जैसे चाहिए कि um, हाँ working condition and if possible we want to withdraw.
We are also sharing in the screen, sir. Ma'am, please see, watch the screen.
बस जैसे जब पेज में आए 10 नवंबर को
Ma'am, you can unmute yourself.
ये उनका कोऑर्डिनेटर पैथोलॉजिकल लाइटिंग इंसिडेंट, ठीक है, उन्होंने सब वही सब मेंशन किया जो मैंने आपको कहा।
नीचे डाउनवर्ड में बोलो ना, नीचे ऑप्शन है।
बोला हूं तो मेरा तो ओपन।
नहीं नहीं, मैंने किया था। हाँ, ये तो आ रहा है।
हाँ
हाँ, ये हमारे यहाँ से आ रहा है।
अच्छा, आप बंद कीजिए। आप बंद कीजिए एक बार।
मैं बंद।
स्टूडेंट मेंबर के क्या होता है,
हटिए ना, मैं बात कर ले रहा हूँ सर।
बात करो।
मैं बात कर ले रहा हूँ।
इसमें स्टूडेंट मेंबर फैकल्टी मेंबर,
हाँ मैडम,
ठीक है, तो ये
अभी आप ही का स्क्रीन शेयर्ड है, अभी आप पीपीटी शेयर कर सकते हैं। पीपीटी को ओपन कीजिए।
केस नंबर 0124 केस का नंबर है। और
हाँ बस। अभी मैडम देखिए ना, यहाँ पे स्लाइड शो जहाँ पे है,
हाँ,
उस स्लाइड शो में क्लिक कीजिए।
नहीं, स्लाइड शो तो मैंने कर दिया है।
नहीं, स्लाइड शो नहीं हो रहा है मैडम, एक्चुअली आपका टोटल पीपीटी दिख रहा है।
अच्छा,
वहां पे ऊपर देखिए, स्लाइड शो एक ऑप्शन आ रहा है।
नहीं नहीं, वो तो इसमें ही शेयर आता है ना।
नहीं नहीं मैडम, स्लाइड आपका पीपीटी जो है, पीपीटी का स्लाइड शो दिखाएंगे तो फुल स्क्रीन में हो जाएगा।
मेरा इसमें तो आ रहा है, बट पता नहीं इसमें क्यों नहीं आ रहा है। क्योंकि मुझे यहाँ पे स्लाइड शो में ही दिखाई पड़ रहा है।
अच्छा, आप एक बार चेंज कीजिए तो स्लाइड को, एरो एरो
हाँ,
बटन क्लिक
चेंज
करके।
किया।
दिख रहा है अनी मैडम?
चेंज किया मैंने।
नहीं, एक्चुअली मैडम आपका इंटायर विंडो शेयर नहीं है।
अच्छा, गिव मी 2 minutes, आई जस्ट लीव द मीटिंग एंड अगेन ज्वाइन एंड देन सी। हाँ।
ओके ओके मैम, ओके मैम।
मुझे ये वाला करना है।
ओके श्योर हो गया ना
आ, अच्छा, अब अभी दिखाई पड़ रहा है क्या? हेलो?
Yes, ma'am. Yes, ma'am. It is visible, but your entire window is not shared, I guess.
हाँ, अभी?
अभी भी नहीं दिख रहा है मैडम। अपना आपका ना जो शेयर बटन है उधर वो एंटायर विंडो में क्लिक करके शेयर करना होगा।
अच्छा, आई ट्राई अगेन।
स्लाइड शो प्रेजेंटेशनটা করতে
वहां पे स्लाइड शो करिए ना। नहीं, अभी तो चला गया।
शेयर में ऊपर वाले
ये
ये नहीं ये तो आप स्क्रीन शेयर कर रही है ना
नहीं, स्क्रीन नहीं शेयर
प्रेजेंटेशन करना ना
प्रेजेंटेशन, ये वाला प्रेजेंटेशन या तो फिर लेना पड़ेगा ना हमको। प्रेजेंटेशन
हाँ।
बंद हो गया, स्क्रीन वाला प्रेजेंटेशन नीचे।
नहीं उसमें तो वही है
हाँ, इसमें से खोलना पड़ेगा प्रेजेंटेशन। इस स्लाइड में जाके नहीं नहीं, ये वाला स्क्रीन में जाएंगे।
डॉक्यूमेंट्स में कहाँ पे बताइए
डॉक्यूमेंट्स में तो नहीं है, आपको ड्राइव में जाना पड़ेगा। नहीं नहीं, आपको ड्राइव में स्क्रीन में नहीं जाना है, क्योंकि मैं स्क्रीन खोलूँ क्या? ये वाला तो
अभी कुछ दिख रहा है क्या अभी कुछ दिख रहा है क्या पार्टी फ्रेंड करना इस
आर यू एबल टू सी नाउ?
के लिए अलग से लाइट है।
मैडम स्लाइड आपको शेयर करना होगा। हाँ हाँ, वही बटन फ्रॉम करेंट।
अभी दिखाई पड़ रहा है आपको?
अभी भी मैडम आपका एक ही जगह पे अटका हुआ है। आप शेयर नहीं कर रहे, मतलब वही पूरा टोटल स्क्रीन दिख रहा है लेफ्ट
नहीं
साइड
तो
में आप।
फिर प्रॉब्लम क्या होगा ना कि हम मुझे उसमें
शेयर में तो हम लोग यहाँ पे शेयर कर रहे हैं वहां पे दिख नहीं रहा
अगर आप चाहते हैं तो हम लोग इधर से शेयर कर देंगे मैडम, और आप देख के बोल सकेंगे।
नहीं नहीं, वो तो ठीक है, लेकिन हम फिर लिंक कैसे देख? लिंक हम उसमें बहुत सारा हाइपर लिंक्स डाला हुआ है।
मतलब आप लिंक से वीडियो चलाना चाहते हैं क्या?
हाँ, सॉरी।
लिंक से हाइपर लिंक से कनेक्ट करके आपको कुछ दिखाना चाहती है
हाँ, हाइपर लिंक से भी कुछ कुछ कनेक्टेड है स्लाइड्स।
आप मुझे वो हाइपर लिंक वाला भेज दीजिए मैडम। जहां पे जरूरत पड़ेगा वहां पे हम लोग उस लिंक में क्लिक करेंगे तो इस स्क्रीन में भी दिखेगा।
ठीक है ठीक है, मैं तब तक आपको भेज देती हूँ, है ना?
यस मैम, यस मैम।
हाँ, तो कोई मेल आईडी पे भेजूं? किस पे भेजूं?
व्हाट्सएप पे भेज दीजिए मैडम। आशीष सर को भेजिए, हम मुझे मिल जाएगा।
हाँ ठीक है, तब तक भेजती हूँ। तब तक यार ट्राई करते रहते हैं, अगर हो गया तो ठीक है।
दिख रहा है
ठीक ठीक ठीक, ओके मैम।
हाँ ठीक है।
कभी कभी नेट इसका इशू होता है टीम्स का इशू
पता नहीं अब ये सब क्या सिस्टम्स, कभी समटाइम्स इट वर्क्स नाइसली, समटाइम्स देयर इज एन इशू। जस्ट गिव मी अ मिनट, मैं तुरंत शेयर कर
पूरा
रहा हूँ।
कॉलेज वाला क्लास
मैडम मैडम,
हाँ बोलिए। हाँ,
और एक चीज बोल रहा हूँ, वो जो वीडियो आप दिखाना चाहते हैं ना वो भी भेज दीजिए।
नहीं नहीं, वीडियो मैं नहीं भेज रही हूँ, स्लाइड्स आर ओनली इन हाइपर लिंक।
नहीं नहीं, स्लाइड्स हाइपर लिंक, लेकिन उसमें हाइपर लिंक में क्या कोई वीडियो या दूसरा
नहीं
कुछ
नहीं,
है?
वीडियो नहीं है, वीडियो नहीं है। मेन से स्लाइड्स हाइपर लिंक में जाके क्लिक करने से एंड बैक जाने से हो जाता है। मैं एक बार शेयर कर रही हूँ, आप देख के
आप
समझ
मुझे एक बार
जाए।
शेयर कीजिए, मैं देख के समझ जाऊंगा। ठीक।
मैं तुरंत दे रही हूँ। हाँ
नहीं खुलेगा मैडम आपका नहीं खुलेगा तो
हाँ।
ये हाइपर ये आपका लिंक रहेगा ना आपको पीसी में है ना वो खुलेगा नहीं मुझसे आपका किसी का वो खोल नहीं पाएगा आप
ये
अगर
सब
नेट का देंगी तो नेट का खुलेगा
देख देख लेते हैं एक बार। लेट मी ट्राई। लास्ट मोमेंट हिचेस जो है ना। मैंने व्हाट्सएप में भेज दिया, आप एक बार देख लीजिए।
Okay, ma'am. I am
Yes,
getting,
ma'am. Yes,
sir.
ma'am.
हम जनरेट
I
करोगे?
got it. I transferred to other person.
मैं नहीं बोल रहा हूँ।
Madam,
And
can you see the PPT?
yes, I can see the PPT.
ओके मैम, देखते हैं हाइपर लिंक वाला क्या बोल रहे हैं, वो भी देख लेते हैं।
इसके नीचे फॉर एग्जांपल देखिए, ऊपर में GHG लिखा हुआ है ना, विच इज इन ब्लू कलर।
हाँ, ये तो लीजिए जी।
हाँ हाँ, फिर बैक बैक
हाँ
जाइए।
हाँ हाँ, हाइपर लिंक है मैम, कोई इशू नहीं
हाँ
है।
हाँ हाँ हाँ, ठीक है ठीक है। तो आप अभी 2 मिनट के लिए आप बंद कर दीजिए, मैं तब तक यहाँ
मैडम,
से।
आप 6 बजे आप स्टार्ट कीजिए, मैं इसको खुला ही रख रहा हूँ, ऐसे ही शेयर ही रख रहा हूँ, इसी से स्टार्ट कर देंगे, स्टार्टिंग पेज में जा रहा हूँ।
अच्छा, तो फिर मैं यहाँ से ट्राई नहीं करूँ शेयर करने का?
नहीं 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 मैडम, वो तो हाइपर लिंक तो हो ही रहा है, कोई इशू नहीं है तो।
ठीक है, चलिए, ओके ओके।
Ma'am, actually the time is from 6 p.m. and now 6:43. So we are starting the session from 6 p.m.
Good evening to all the distinguished participants, respected faculty members, and invited guests. I am Dr. Ayani Nandi. On behalf of Ramgarh Engineering College, truly delighted to welcome you all to day 5 of our faculty development program on alternative fuels and hydrogen energy, clean energy innovations for sustainable society. After an enriching and insightful fourth day, we are excited to continue our journey of learning, exploration, and knowledge sharing. Today's session promises to bring even deeper perspectives, practical understanding, and expert-driven discussions that will further strengthen our grip on the emerging trends and innovations in this domain. Your active participation, curiosity, and engagement have made Day 4 truly successful, and we look forward to the same enthusiasm throughout today's schedule as well. Let us begin Day 5 with a new energy, open minds, and shared commitment to advancing our academic and professional excellence. Today we will take a group photo on 7:35 p.m. So I am requesting everyone to keep your video on that time. Wishing everyone a productive and inspiring day 5 of the FDP. Today I would like to briefly highlight the importance of academia-industry collaboration, an essential pillar of innovation and sustainable development. When academic institutions and industries come together, they create a powerful interaction where cutting-edge research meets real-world application. Academia provides deep knowledge, fresh idea, and skilled talent, while industry offers practical challenges, advanced technologies, and opportunities for implementation. This partnership helps bridge the gap between the theoretical learning and industrial needs, making education more relevant and industry more innovative. Through joint research projects, internship training program, and technology transfer, both sectors can accelerate progress, enhance productivity, and address critical societal challenges. In today's fast changing world, such collaboration is no longer optional, it is a necessity. Let us continue to strengthen this partnership so that our students, our industries, and our nation can move forward towards together a more innovation and sustainable future. It gives me great pleasure to extend a warm welcome and heartfelt welcome to our esteemed guest, Ms. Preeti Jha Madam, General Manager, Environment, Conservation and Sustainability at Bokaro Steel Plant, Steel Authority of India Limited. Ms. Jha Madam is an accomplished metallurgical and environmental professional with over 30 years of the distinguished service at SAIL. Her career is a remarkable blend of research, technology development, marketing leadership, and environmental within one of the country's largest integrated steel plant. In her current role as general manager, she leads the environment, conservation, and sustainable initiatives at Bokaro Steel Plant. She has been at the forefront of the implementing center of the environmental compliance and reduction emission, minimizing waste generation, promoting water conservation, and strengthening sales, the larger mission of the green and sustainable steel making. Under her leadership, the plant continues to advance ISO 14001 environmental management systems and integrate sustainability deeply into the operational practices. Her past role include serving as Deputy General Manager at SAIL Central Marketing Organization, where she the interference between the production units of the customer requirements, ensuring the technical excellence and product quality. Previous to that, at SAIL, prestigious Research and Development Center for Iron and Steel, RDCIS, she contributed significantly to applied research in physical metallurgy, steel, microstructure property relationship, and process improvements that enhanced steel quality and productivity across the various SAIL plants. Ms. Preeti Jha Madam began her journey with SAIL in 1993 as a management trainee technical and has since demonstrated classic leadership, technical expertise, and unwavering commitment to sustainable industrial development. She holds a BTech in metallurgical engineering from BIT Sindri, one of the country's primary institute. Today, we are truly honored to have Ms. Preeti Jha Madam with us. Her vast experience, deep technical insight, and passionate advocacy for environmental conservation will undoubtedly inspire all of us as we explore the pathways towards sustainability and responsible industrial growth. On behalf of the organization and organizing committee and all the participants, I, Dr. Ayani Nandi, warmly welcome you, ma'am, and look forward to your valuable insights. I also welcome all the faculty members and participants who have joined us with great curiosity and enthusiasm. Let us begin today's session with a spirit of learning, collaboration, and innovation. May I now request you, madam, to kindly share your thoughts and inspire us with your words.
Thank you, madam.
Thank you, ma'am. Ma'am, can I share your PPT?
Yes, please.
Is it visible?
Yes, it's visible
Okay.
to me. Thank you. First of all, I would like to thank you, ma'am, for your kind introduction, and also the organizing committee. And I hope to do justice to the job that has been bestowed on me by, and the honor that has been bestowed upon me by the organizing committee. So thank you. The Atal Online 6-day Faculty Development Program 24-25 has been, today is the 5th day. And for past 4 days, we have been having very interesting sessions by various speakers, various eminent speakers. So they have spoken about on different topics, which was very informative for us all. And I'm sure it would have been informative for you also. Today, what I intend to do through my presentation, can we have the next slide, please? What I intend to do through my presentation is that I would like to tie the various loose ends in the way that we have used various terms during all the speakers have used several terms like carbon footprint, greenhouse gases, net zero. But I would like to share with the House, I would like to deliberate on what these terms actually mean and how they have generated over time and how they are going to affect us. And I have spent all my working life, all my career in Steel Authority of India Limited. So my basic area of work is steel making. So as we go ahead to deliberate on how we can work with how industry and academia can work together, but it will be more in the context of steel industry. And hence, I would just like to take you through the processes which will help you to understand the problems of steel industry and where we need to work together, how do we collaborate together. So the overview of the steel industry will help in building up the work for what we will be discussing ahead. So we'll also discuss the key decarbonization pathways for the integrated steel plant. And what industry, academia, why should we collaborate, and how collaboration can be structured, what could be the enablers, that we will also discuss. Can we have the next slide, please? So we all talk about the carbon emission, but carbon dioxide is not the only demon here. There are other gases, the greenhouse gases, which we call them, which are responsible for greenhouse effect. So these greenhouse gases are carbon dioxide, methane, ozone, water vapor, nitrous oxide, hydrofluorocarbons, perfluorocarbons, and sulfur hexafluoride. These gases are all responsible. In fact, if we take the emission factor, then worst among all the gases is sulfur hexafluoride, which has a very high factor by which the emission takes place. But everyone talks about carbon dioxide. Why? Because carbon dioxide forms almost 80% of the total greenhouse gases that is being emitted by which is given out by different ways, or like fossil fuel, through fossil fuels, or normal human activities also. Ma'am, could you just click on the hyperlink? Yes, please. So in this slide, you can see the percentage of gases. So carbon dioxide and total carbon dioxide emissions, whether it be by land use or fossil fuels or industrial processes, is nearly 80%. We can say methane is 16%, nitrous oxide 6%, and other fluorocarbons, which we are talking gases, are only 2%. That is why people don't talk about these gases much. But there are various parameters which also talk about greenhouse gas emissions. We can go back, ma'am. We can generally they talk about all greenhouses together. So I will be talking about that also. And these gases, when they are present in the Earth atmosphere, they cause greenhouse effect. So what is greenhouse effect? It is a natural process that warms the Earth's surface. It occurs when the gases trap heat from the sun, preventing it to from escaping back into the space. So these gases allow sunlight to enter the atmosphere, but absorb and re-radiate the heat and that are absorbed. So because of this, the overall temperature increases inside the Earth's atmosphere. So is greenhouse effect a bad phenomenon? The question would come to that. No, not at all. Because greenhouse gas is, these gases only, this greenhouse gas effect only helps to maintain the Earth's average temperature. Without this effect, without this phenomenon, it is, as per one study, the temperature of the Earth would be around minus 18 degrees centigrade, instead of the current average, which is around 15 to 20 degrees centigrade. So there was a scientist by the name of Eunice Newton Foote. She was an American scientist from, I think, in some 18th century, 1850s or something. She was the first, she was the pioneer in doing experiment on carbon dioxide and stating that carbon dioxide traps heat. But somehow over a century, her contributions were overlooked, and it is only very recently her name has started coming, being recognized. But generally, otherwise, John Tidal has been getting this honor that he has been the pioneer. So then another thing is there are two types of greenhouse gas effect. One is natural, other is enhanced. Natural is perfectly okay. It is from the entire process of the Earth. For example, if human beings are living on the Earth, the normal activities of the human beings, animals, they also emit carbon dioxide. So all that is okay, and that helps to maintain the basic temperature on the Earth. It is the enhanced greenhouse effect due to the human activities, so which causes problems, especially the burning of fossil fuels like coal, oil, natural gas, deforestation, industrial processes, and these all lead to the climate change, Like we have heard recently that the sea levels have been rising. We hear so many changes in the weather pattern, that the temperature, summers are very hot, or too much of rain, or too many storms, tornadoes. These are all attributed to climate change. So carbon footprint, when we talk about carbon footprint, is the total amount of greenhouse gas emissions. Primarily carbon dioxide. Why primarily carbon dioxide? Because it is, as I have already said, that it is the 80%. And we can also have carbon footprint of a specific activity or a specific product, or we can also have carbon footprint for us individuals. So I would take this opportunity to request all of us to think about it, how much carbon footprint we are generating as individuals, and how we can contribute to the environment by lowering our carbon footprint by simple steps. I'm not asking anybody to stop using electricity or electrical equipment, but by small steps. So then coming to net zero emissions. Net zero emissions we have been talking about every day. This term came into being a long time back, and it can be traced back to a lady called Myles Allen, who published a paper highlighting the overall impact of cumulative emissions of carbon dioxide on global warming. So after the net zero term became more popular after the Paris Agreement, that is the COP, COP meeting that was held in 2015. We'll talk more about COP meetings later on. Why it is important. Paris Agreement is one of the most important COP meetings. We can consider it as a milestone. So what is net zero emissions? It is a state where the amount of greenhouse gases released into the atmosphere is balanced by the amount that is removed. This is achieved by first reducing the emissions as much as possible, and then offsetting the remaining residual emissions through various carbon removing methods, like we can have by tree plantation is the best method, or by CCUS. I think we'll have a session on CCUS later in the day today. So this is net zero emission. And this came into being from this during that Paris Agreement, which I spoke about. While when we talk about carbon neutral, it means only carbon dioxide net zero. But it is, when we talk about net zero, it means that we are applying to all greenhouse gases, including methane and nitrous oxide. Next slide, please. In this slide, I have tried to share the data where we have global emissions on one side. In the first chart, you can see carbon dioxide emissions, and on the left-hand side, we have the atmospheric carbon dioxide. Global carbon dioxide emissions have reached record high in 2024. Reaching a quantity of 37.41 billion metric tons. And it is expected in 2025, it will increase by another 1.1%. Can we have the hyperlink, global carbon emission? Yeah. So here we can see that in 2025, it is forecasted that it will increase by 1.1% to 38.1 billion. But despite this increase in emission from all activities, the overall CO2, it has marginally decreased, which is a good news, at least. And this is because of use of renewable energies and forestation related. I think I've written it wrong. It is forestation related activities. Can we go back, please? And we can also see the record high of carbon emission basically started with industrialization process somewhere in 18th century, and then it has been steadily increasing, and it was highest recorded was in May 2025 of 430 ppm, which is actually almost more than doubled. And this has been attributed to various activities like human El Nino effect, forest fires, and all. We might have like a if we have too much negative, but we try to think negatively, then there might be a question that how is this carbon dioxide slight increase in ppm, how is it going to affect? But a simple example will prove that how carbon dioxide is affecting our atmosphere and things around us. If you see the solubility of carbon dioxide in the other chart in water, generally oceans, they form the carbon sinks. And this increase in carbon dioxide in the atmosphere has been causing ocean acidification, because carbon dioxide reacts with water molecules to produce carbonic acid. And as per certain studies, lowering of ocean pH has happened from 8.21 to 8.10. And this minor effect also affects the marine life. Can we have the hyperlink on 8.21? Yes, you can see in this, I could get one picture of how it has affected the ability of marine life to extract calcium from seawater and build skeleton or shells. You can see the two different pictures. One is the healthy shell, other is the damaged shell. So even the small snails, ocean snails are getting affected. So once it goes into the ecosystem, it is going to make more and more difference. Can we go back? Next slide, please. It is this slide we have shown because it is a very interesting factor that which countries are the highest emitter of carbon dioxide on one side, and on other side it is the per capita carbon dioxide emissions, which again is a very important data. So if we see that China is the highest currently highest carbon dioxide emitter, followed by US and India. Actually, earlier, United States was the highest emitter, but in 2005, it was overtaken by China. And India is also not very far away from increasing trend in the carbon dioxide emission. United Nations, United Kingdom, it was where carbon dioxide emissions started in form of industrialization, and slowly but now they have found a way and it is tapering down. But it is interesting to see that China's economy has been expanding rapidly, and therefore consumption of fossil fuels have also been increasing, and therefore their carbon dioxide emission has increased. But if we see the per capita consumption, highest is United States, followed by Canada. India is very down in the very at a lower level. India, in spite being home to a population of around 17%, we are contributing to total GHG of only 4% in the world. So this is also a factor which generally we don't talk about. This is an important point, that per capita consumption, if we see, sorry, not consumption, because I'm from steel, I always talk about steel consumption. So I uttered those words. per capita carbon emission in 2023 of India was around 2.07. And in 1970, it was 0.4. Whereas China in 2023 was 9.24. There are countries like Qatar, which have one of the highest per capita consumption. You would think it would be USA, but it is Qatar with 43.5 tons per person. Can we change this slide, please? So United Nations Framework Convention on Climate Change is an international treaty adopted in 1992 to prevent the detrimental or the dangerous human interference with the climate system, and under which the Conference of Parties, which we generally refer as COP, COP actually, is the supreme decision-making body in the convention. So COP1 was the first meeting that was held in Berlin, 1995. And then the Paris Agreement, which we were talking about, was COP21. And the historic decision was taken to aim to keep global temperature rise to well below 2 degrees centigrade, above pre-industrial levels, and to pursue effort to limit it to 1.5 degrees centigrade. And in COP26, which was held in Glasgow in November 2021. So in this meeting, India took a giant step of committing to net zero by 2070. And our government has given 5 full strategies, which is called Panchamrit goals. I remember someday one of the participants had asked a question on first day that why India has asked for net zero emission by 2070. See, during the COP meeting, it is everyone has to voluntarily, depending upon the conditions of the country and how much they can commit to go, they can make their own decisions about reaching the net zero. So India has committed for 2070. Very few countries have, like Maldives, they have committed for 2030. China has committed net zero for 2060. And countries like US, Canada, Japan, they have committed for 2050. And if we come even earlier, it is Australia and Iceland, which have committed net zero by 2040. China and India, it is difficult for them to commit because we are growing economies. Particularly if we talk in respect of India, we are very growing economy. Our infrastructure is developing. Lot of steel work is being done. And as we go down, we'll see that the national steel policy is very ambitious policy to produce 300 tons of steel. So if the steel production goes up even more, there'll be more CO2 emission. Can we change the slide? Steel is considered as the backbone of our infrastructure. Why? Because everything you see around you is made of steel. So in SAIL, we have a tagline that there is little bit of steel in everyone's life. So if going by that tagline, steel is there in everyone's life. In our homes, in our industries, even the renewable energy which we were talking about, it is impossible to have the infrastructure for renewable energy without steel. For example, if we talk about wind turbine would require, every wind turbine on an average would require something about 140 to 180 tons of steel, because steel is required for making towers, nacelles, foundation, etc. Even for solar power or hydropower or even geothermal power, what we talk about, average steel requirement is 20 to 30 tons per megawatt. on an average. Steel is a very steel role is becoming more and more crucial in coming times. And we say that steel is sustainable because can you hyperlink please? We say that steel is a sustainable, has got a sustainable future because of certain reasons. Sustainable future पे जो है क्लिक करिएगा. नहीं. Can we go back please? Sustainable future. जो ब्लू में फर्स्ट लाइन पे है ना, सेकंड लाइन पे. Steel is the one of the world's most recyclable material. 100% steel can be recycled, and the best part is when steel is being recycled, then most of the carbon emission is very low. Then 90% of the water that is used in steel industry can be treated, cooled, and returned and reused. The energy that is used for production of steel has been reduced in 61% by 61% in last 50 years. And then is the development of high strength steel. Can we go back please? So steel is a very it can be used in very different way. It can have different strength, different properties, and therefore it has got various applications. So by having designing higher strength steel, we can have less and less use of steel, and that is why we consider it as it is important for sustainable future. But the irony is that steel is one of the most polluted industry, which globally steel industry contributes to 7 to 8% of total carbon emission. And in Indian steel industry contributes around 10 to 11% of total emissions here. So in year 4.1 billion tons of CO2 was emitted by steel industry in 2004. Can we go to next slide? Yes, thank you. As we can see, India right now is in 2024, it has produced 149.6 million tons of steel, and it is the second highest producer. Whereas China produces around 1,000 tons, more than 1,000 tons of steel. And we are aiming, as per the National Steel Policy 2017, we are aiming to to produce 300 tons of steel by 2030-31, and a per capita consumption which is currently 97.7 kgs. We plan to increase it to around 100 and I think it is I forget. I think it is 106 kgs per capita consumption. So whereas global per capita consumption is 219 kgs. So sorry, it is 160 kgs. We aim to go to 160 kgs by 2030-31. So in 2024, steel industry emitted around 366 million tons of CO2, and average emission is 2.54 tons of CO2 per ton of crude steel, which is much higher than the global average. Now, if we talk of green steel, everyone talks of green steel. So what is green steel? India has been one of the pioneers to develop a definition for green steel, and taxonomy of green steel was announced on 12th December 2024, as per which any steel industry any steel having product having emission of more than 2.2 is not eligible to be called a green steel. So for being a green steel, it has to be below 2.2. And under green steel also has been categorized into 3 categories: 3-star, 4-star, 5-star. So and this will be revised. This will be revised every 3 years. Can we go to next slide? there are basically three methodologies I have put on this slide so that you can compare the processes. So most popular process is the blast furnace and basic oxygen method, and 70.4% of the global production is through this method. But as we can see, the average CO2 emission is 2.66. There are two CO2 emission per ton crude steel levels that I've given. One was as per the World Steel Association's original indicator. World Steel Association has very recently made a change in their calculation methodology, because there are different methodologies. People get confused, but World Steel we generally follow because it is a widely accepted methodology. So as per it, they have recently included methane and nitrous oxide as their emission, and they have also included upstream scope 3 emissions from mining operations. So we can consider it as 2.66, and energy used is 24 gigahertz. So, but if we consider the electric arc furnace, which is 100% scrap based, then the emission per ton of crude steel is 0.71, and 21% of steel is produced through this route. The reason being that the scrap availability is very low, and in India specifically, scrap is of basic concern. There has been recently changes in the policy so that scrap facility can be, and the scrap we can get more scrap from the economies that are already developed, because India is a developing economy. It will take some time for scrap to come back into that quantity of scrap to come into circulation. Then the third category is through DRI EAF route, but DRI is through natural gas. So if we have natural gas, then the CO2 emission is 1.66, and energy used is 22 gigajoules. So natural gas again is not available in India at very cost-effective prices, and especially in the eastern part it is not available. In western part still some it is there. Therefore, these two methods of electric arc furnace and the natural gas DRI-EAF is not very popular in India. And BOF route is the. Can you click on this hyperlink? Here we can see that blast furnace BOF route in India is around 42%, 43% of steel is produced through this route, whereas EAF route is 21.9%. Even though we can say that this EAF is not 100% scrap based. It is mostly DRI, sponge iron based. And then we have the EIF, induction furnace based. Which is the 35%. So India is one of the largest sponge iron producers also. Can we go back? Next slide, please. As we have seen that blast furnace is the blast furnace BOF is the most popular, cheapest, but the most polluting process of steel making. And why is this so? Because if we see the steel process into we add carbon in form of coke or coal for production of hot metal in a blast furnace. So the coke which we add here, the carbon which we add here, it not only acts as a fuel, it also acts as a reducing agent. So there is a dual purpose. So in one of the, if we have the best optimum working parameters, then we can see that the coke added is around 300 kg per ton of hot metal. If this is in case of very optimum use of all parameters. If the blast furnace is in not very good running condition, then this coke rate goes high. And then there is a pulverized coal which is added around 200 kgs per ton of hot metal. And then we we have limestone, and then which might have some carbon, and then the burden charges. So the carbon here reduces, and then we get hot metal, pig iron, and slag. And then there are rest processes also, which but most of the CO2 is emitted by the hot zone, that is the blast furnace, then SMS, that is the BOF, or sinter plant, and coke oven. So 80% of the CO2 in a steel plant is produced at till this level, and rest of the processes like rolling a mill and all is responsibility is only about 15 to 20%. Can we go to next slide, please? Next slide, please. Yeah, so in this we can see, in this slide we can see that the coke has around 87% of carbon, and coal, the pulverized coal which is being added through the is 78% carbon, and ultimately in the hot metal will have around 45 kgs of carbon only. So balance of carbon is going out. So it is very easy to calculate CO2 emissions from the blast furnace by using different methods. We can use mass balance method, or we can use emission factors. Mass balance method could be by total carbon input and then subtracting the total carbon output to find the net carbon emission, and using carbon emission factors, which is pre-decided. So we can use that technology. Can we go to next slide? So you can see a comparison of different processes in the hot zone, and how much CO2 is being emitted by them. So blast furnace is responsible for 70% of the CO2 emission. So the carbon being the main culprit, as I had said earlier. But blast furnace even will remain relevant, and it till 2050 or maybe even more. The new facilities that are coming up in steel plant, they are also putting blast furnaces, because it remains relevant in spite of having high pollution, because of high production capacity, cost effectiveness, and the ability to produce consistent quality of iron in continuously. But industry is working in various ways to reduce this emission in the from blast furnace particularly. This could be in by means of technological advancements, like for using more pulverized coal injections, or by oxygen enrichment, or by some other process, or by emerging technologies, for example using hydrogen in place of coal for replacing, or biochar. Everyone is talking about biochar these days, and some people have also, some industries have also done trials with recycled plastic. And then the most important one is the carbon capture, which everyone is talking about, carbon capture, utilization, and storage. And it is expected that blast furnace will remain relevant for a longer time. So we have to work on various innovations to mitigate the environmental effect of these blast furnace. Yes. Can we have the next slide? So I have tried to note down these few areas where lot of work is required in terms to decarbonize and make and go on a path towards net zero. So some of these areas we'll be discussing, and these will be the areas where we can, why I have given a backup information. I have spent so much time explaining about steel industry, is because these would be the areas where the industry and academia collaborations can take place, which we'll be discussing again. So the first point is reducing fossil carbon in iron making. So reducing fossil carbon in iron making can be achieved through substituting fossil fuels with either hydrogen, like I was telling you. I also spoke about biochar, or adopting alternate technologies like electrolysis. But all these other technologies are at very nascent stage. Even the work with hydrogen, replacing fossil fuel with hydrogen, is also at a very nascent stage. We at Bokaro Steel Plant have planned for trials at one of our blast furnaces, where we will be injecting hydrogen. Then with hydrogen comes the problem of having green hydrogen, because it is important that we have produce enough hydrogen, green hydrogen. Otherwise, the very reason why we are using hydrogen will be lost. Then, for example, then biochar, I can tell you about a trial which has already been done at Durgapur Steel Plant, where biochar was used in sinter plant. It not in blast furnace, but in sinter plant, where 100 tons of biochar was used for one. 300 tons of biochar was used for 1:1 replacement. But one has to be very particular about few things when biochar is being used. One is the cost of biochar, right? And steel industries are massive areas where huge quantities of raw material is required. So can we get raw material in these quantities? That is another point of concern. Then is the cost of biochar. The trial which was done at Durgapur, they got biochar from Gujarat. It does not work out commercially. So therefore it is in trial stage. So any experiments or any trials, it has to be successful, has to be accepted commercially also. And for biochar, it has to have certain calorific value, say around 8,000, minimum at least 7,000 calorific value should be there. So these kind of trials are being done, and these are the areas where we can work further. Then in area, if we talk about energy efficiency, can we have hyperlink on energy efficiency? We see the best available technologies, people who are using the best available technology there, the energy, specific energy consumption is around 4, right? 4 gigacalories per ton of crude steel. But in the current average, it is around 6.5. So there is a huge difference. A lot of work. Can we go back? Back, please. So a lot of work needs to done in this area also. Energy efficiency can be achieved by optimizing production processes, improving equipments, adopting new technologies to reduce high energy consumption and associated costs. Some of the areas where we can reduce is by having a proper gas network management. During the process of coke making or hot metal making or even steel making, that is in BOF, lots of gases are produced. So this LD gas, BOF gas, coke oven gas, these are again being reused to reheat, because it has CO as well as CO2 mixture. So it is being reused. So a proper effective management of this. We have lime kilns where lime is calcined. So in these kilns, we have earlier we were using tar as fuel, but now we have started using these gases, these fuel. So the more we use these gases, more we utilize that. This will help us in improving the energy efficiency, and as the energy efficiencies will become better, automatically the CO2 emission factor will go down. Then equipment upgrades. Then using VSD, variable speed drives on motors or fans or pumps, which are used with variable loads. So I think we have also had many sessions on IoT, where all this area has been explained earlier. So I will not go into details of that. Then digitalization is a very big way how we can increase efficiency. So digitization also, I think we had a session. Then coming to material efficiency, that optimum amount and quantities of raw material should be used, and so that optimum quantity of wastes are generated. Steel plants generate lots and lots of waste. LD slag is there, blast furnace slag is there. There's so much fines are being generated. So it becomes, under material efficiency, under circular economy, it becomes very important how we utilize all these wastes. At blast furnace, at Bokaro Steel Plant, we have been using blast furnace 100%, and we are trying to use maximize our use of LD slag also. And then from the different sludges, we have had trials where we made bricks out of this sludge and mixing some binder in it and some small quantity of iron fines, and this was again charged back into the SMS, that is the BOF. So and then the fines which are generated, this can be used for micro pelleting, briquetting, and this will and again charging into the system. So this will not only help us in being more efficient, it will bring our costs down, it will have an impact on environment by terms of CO2 or greenhouse gas emissions also. Then is the best available technology. It is not always very easy to have to change the technology of a plant every now and then, because steel plants are very high investment is required. High investment is required for any processes to be upgraded or new technologies to be got. For example, in coke oven, nowadays the latest technologies of stamp charging, dry quenching, but at Bokaro Steel Plant we do not have any. All our batteries are none of the batteries are stamp charging or dry quenching, but we have planned for a new battery line which will be a which will have stamp charging and which will be dry quenching. Then comes the blast furnace and BOF steel making where we can use various things like LD gas holder, waste heat recovery system, good control systems, and digitization, as you know, is everywhere. The renewable energy, I will not talk much because lot has already been deliberated upon. The renewable energy is not, our country requires to produce lot of renewable energy for everyone to, for us to be able to use it 100%. That day is still a little far away. Coming to carbon capture, utilization, and carbon, if we talk about carbon capture, a lot of work. I think you'll have a session after this. So, but carbon capture is still a technology which is in very much of a development stage. Because even though the idea started in 1938, progresses have been very slow. I was just reading somewhere that there are only 2 large-scale coal-fired power plants in the world, one in US and one in Canada, that have carbon capture and storage technology, and both are retrofitted technology. And as per the International Energy Agency, there are only 18 large-scale CCUS facilities operating worldwide, and they collectively capture about 3.5 crore tons of CO2 per year, and this amounts to only 0.1% of total emissions. So And again, another study says that around 2,700 gigaton capacity carbon capture will be required if to meet the current demands of global environment. Even though it is not possible to capture our carbon and to have so much carbon, because there are certain problems also in this area. One, the costs are very high. It is companies still do not want to spend much on carbon carbon capture. And secondly is the concerns about the availability of sites where this carbon dioxide can be stored after it has been captured. One more area is where CO2 can be being converted into value added products. Lot of work is going on, and I know a few companies in India also who are working in this direction. It can be converted into fertilizer, carbonated drinks, or one very interesting idea was coming around is that it can be infused into the wet concrete also. Which help to cure it, which helps to cure it. So all these ideas are there. A lot of work needs to be done in these areas also. Then if we talk about alternate fuels, alternate fuel is again, we have already spoken that there is hydrogen. For carbon capture, I would like to say one thing. I think I missed out on one point, is that trials are being done with different kind of electrodes. Because there is a problem that wherever the concentration of CO2 is less, then capture from that is also very difficult as per my information. So people are working on MOFS nowadays, that is the metal organic frameworks, they call it, which behaves like a sponge. So all these areas are where our academia can come in big way and help us by addressing these issues and helping India achieve 2070 net zero targets. If we talk of scrap, as I had already said, scrap is in is not available in large quantities in India. It will be still some time before it is available. Many countries have started putting kind of restrictions. I'll not say ban, but kind of restrictions on use of on export of scrap. India is among the highest importers of scrap, but scrap is why 100% scrap can be used, because magnetic properties of the scrap helps us to differentiate it with the separate it from the waste streams. And every ton of steel scrap, this is a nice bit of information which I found on WSS site, which says that every ton of steel scrap used avoids emission of 1.5 tons of CO2 and avoids consumption of 1.4 tons of iron ore and 740 kgs of coal and 120 kgs of limestone. So how we go ahead in this direction, it is still to be seen. Some nations have very well established scrap supply, but all the government in the world are striving to meet that climate target, and therefore they have put restrictions on export, as I have already said. Then coming to alternate fuels. Alternate fuel is like hydrogen, then electrolysis, what we were talking about, that electrolysis can be used for the electrolysis actually uses water. Iron uses electricity to split iron ore into iron and oxygen, eliminating the need of carbon-based reduction, which actually happens in the blast furnace. Then digitization, in all procedures, if digitizations can be used to optimize process optimization and material innovation. We have been doing some work like trying to have AI based material loading in the blast furnace, but this is also in very trial stage, very initial stage. A lot of work still needs to be done. Can we have the next slide, please? So now we come to the fact where we talk about industry and academia collaborations. Industries can these are for why it is important, why this collaboration is important. We can work in all the areas that I have been speaking about. We can work in all these areas where we can industry and academia can collaborate in all the areas mentioned above. But why it is important? Because innovation and scale is the first point. That many of the technologies, like for example, green hydrogen, carbon capture, then digital optimization, all these routes are still emerging. A lot of work needs to be done before it can be actually translated into an industrial level. So academia can help to develop and pilot them. Industry can then deploy them at a scale. And in the steel industry, everything is in very large scale. So here it comes their importance. Then bridging knowledge gaps. Steel plants may have a lot of operational experience, but the experience regarding fundamental knowledge of new materials, or the about the process modeling, or about digital twins, we generally don't have that. By we I mean the industry people generally don't have that. So academia brings that on the table. It helps us to bridge that knowledge gap. So fundamental, all information, what is happening latest, that the academia can bring on the table, and industry can then see whether it can be work together to translate it into actual practical working. Then academia, the third point is life cycle and value chain thinking. So academia can help analyze the full scale chain from ore to finished steel to recycling, and quantify emissions, material flow, and embed the circular economy thinking. Then training and skills, everyone talks about this generally. We can learn from each other. I think that is more than said, that we can all learn from each other. We can learn from the academia, whatever, how to go ahead, and then the practical aspects of the steel making we can share with the academia. Then the shared risks is the emerging technologies are risky. They are also expensive. So joint collaboration will distribute the risk. It will be between the industry and academia, and investments are high. So for any work that is being done, so this also can be shared because. Then policy and standard developments is where academia can play a very, very big role. As I said, that calculation methodology, or how to measure CO2, all these methodologies there are so many methodologies coming up, some given by the government, some given by the private organizations of repute, of course. But a person, whether even we sometimes being in the environment group, we also sometimes get confused. which policy we must follow. Sometimes we have the WSA methodology. Sometimes there will be a B methodology. Now people have started talking about CCTS. Then carbon credit trading scheme. Then every day there is something or the new coming up. There is no set as to what the industry must do, and we being in industry do not have that much liberty of to go into details of everything before deciding. So the academia can help in a very big way by helping to develop one common policy or for the entire all steel plants in India, or maybe having some standards of going about. So this is an area besides training and skills which can be easily done by academia. Then is the government academia industry for related to funding and all. Because the investments are huge, funding is very important. The funding can come partly from the corporates. Ministries are funding in big way. For example, our hydrogen project is partially being funded by the hydrogen mission scheme that is there. So we can so ministries are there to help us, or government is there to help us. We have to take the opportunity and try to transform it into something concrete, so that that will rest on us. Can we change the slide? So mechanism of collaboration may vary. For example, we can have joint centers of excellence in partnership that can align research, education, and innovations, where another thing, we need laboratories for for lots of work, and our laboratories sometimes it is difficult to maintain. So if academia has got good laboratories, that can also be used by the industry. All laboratory based programs can be developed. Then is open innovation and accelerator programs that industry can run, challenge programs in just like a hackathon, or where we allow rapid prototyping, academia involvement. Industries can be mentor in that, and which will help in innovating and going ahead in the process. Then is the life cycle assessment and roadmap building. As I was saying, that policy is an area, policy making, development of standards is an area where we can make. Similarly, life cycle assessment is also another area where and how we can collaborate. Then comes the policy standards and certification, and data analytics. And to go ahead, I can, if I would like to suggest one or two ways. We can have we can divide the entire collaboration into maybe 3 or 4 areas, where one would be, say, one would be, for example, around phase one. Phase would be where we would have the projects which would show results comparatively fast. Say in next 3 to 5 years, we are able to show something. This could be this could be working in the areas like baseline measurement, where academia helps to collect detailed data of plants, correct emissions, fuel energy chains. Then setting up of interim targets, then pilot collaborative R&D projects. All these kind of works can be done for smaller projects. Then we can have another set of projects which could be for the larger period, say for the period of we can work together. But I don't means PSL or SAIL, I mean the industry. So industry can work and academia can work together, say for a slightly longer period, say 5-10 years, which would be like developing successful pilots and then transforming it into these steel plants, actually seeing if it can be, for example, hydrogen DRI route, which can it can be after research work, it can be translated into the trials can be done at plant level also. Then value chain optimization, so the business integration, all these can be done by the for a slightly larger frame. Then another set of work can be done for even larger targets, say for 10 to 20 years, where we can virtually shift to, we can start shifting to low carbon steel making, having maximizing scrap use, material use. This is how, then reporting verification. So these could be the roadmap framework which we can set for ourselves and start working on it. So I think by this we have come to the end of our presentation. Can we go to the next slide? So these could be the enablers, which I have been talking about, like having clear goals, clear common objectives, that what we actually want to do. Then long-term commitments. It is not because short time, if you want to do any major technological changes or developments, it cannot be done in a small time. Then shared investment and risk sharing. Then access to operational data. Of course, academia can only work if the data is operational, and vice versa is also true, that academia share, we are open in sharing information with each other. Then translation research culture. We can have a research culture, then pilot to scale pathways, integration with business strategies. Can we have the next slide, please? So thank you. I would like to say one thing, that my favorite quote, generally people say that for regarding as far as environment is concerned, people say that this we have not inherited this earth from our parents, but we have borrowed it from our children. But my favorite saying is that success doesn't come from what we do occasionally, but what we do consistently. So whatever we decide to do, whatever collaborations, whatever way we are going, even for towards decarbonization, towards net zero, we have to work consistently to get results. Otherwise, it doesn't happen. And okay, I would like to show one more slide before I end. Can we go to the next slide after this? See, none of the steel plants are net zero till now. Okay. Net carbon zero. No, none of the steel plants are till now. The only steel plant which claims that it is the world's first carbon neutral steel plant is the Sao Paulo Brazilian integrated, somewhere in Brazil. I can't pronounce it. But anyway, I think you get to the point that, but you see what the capacity is. It is only 6 lakh tons per year. And here we are talking about single steel plant having 4 million ton, 5 million ton, and now even 8, 10 million ton. Right? So this is only 6 lakh tons. So it is possible, and it produces TMT. So it is possible for them. And what they have done to be carbon neutral. This is the area where we need to focus on. They have renewable power. They have invested in circular use of raw material. Hot metal production is based on eucalyptus charcoal, and in the interesting part is they have replaced traditional coking coal totally, and they have around 50,000 hectares of planted eucalyptus trees around in their premises for continuously being able to generate this charcoal and therefore produce captive pig iron. So it achieved net carbon neutral, we can say, in 2020, negative 0.04 million tons of carbon dioxide per ton of steel raw material. So this is one interesting fact. And do we have a slide below this? Can we show that? Yes. So this is just a general slide. It is not actually a part of presentation, but I just wanted to show what we are doing at our plant lately. So in terms of energy efficiency, we are using in coke oven, we are using surfactant, which helps to reduce the moisture content in the coke. Surfactant is sprayed moisture because it is wet quenching, no, in our batteries, coke oven. So after this we have so surfactant is sprayed. It helps to reduce the moisture content in the coke, and therefore in the blast furnace requirement of fuel is low, and therefore helps in energy efficiency. Then reduction in specific steam and specific power consumption, we are working on that. LD gas recovery, we are working on that. Then renewable power energy, we are trying to get renewable power energy from the grid. And we are also, this point I have missed out here, but we are also having small solar plants. We are giving out orders for small solar plants to be installed within the plant premises also. Then material efficiency is by increasing coke rate, by not increasing coke rate, sorry, by decreasing coke rate, increasing CDI, the pulverized coal injections that we were talking about, using more pellet, increasing carbon enrichment. Then in terms of best available technology, we are having a battery. We will be having a battery in coke oven battery, which will be based on dry quenching and step charging battery. Then is the top the new blast furnace which is being planned at blast furnace will have at BSL will have top pressure recovery turbine. Then I have already told you about the green hydrogen injection in blast furnace. Then is the CCUS technology. I forgot to tell you, we have signed an MOU for with a party which has been conducting trials on the CO2 emissions, capturing CO2 emissions and converting it into value-added product. So it will be, they have done some trials and they have taken gases from blast furnace and coke oven, and they'll be converting it into value-added product. Then is the biochar I have already told about. We are also planning biochar injections in blast furnace. Then is utilization of waste. So everyone, we all try to use the waste that is available. So if this is very important area where we would look forward, all industries would like help from. So especially the fly ash from the power plants. We have power plants, so what is to be done with the fly ash? That is a major issue, one of the major issues again with the waste, one of the waste that is generated. So with this, I think with this we come to end of my presentation. I hope I have been able to add little bit to your information. And yes, please. Thank you. No, all these are not required, madam. You can close the presentation. Uh, In case there are any queries, I would love to answer, or maybe if there are no queries, if you want to interact, you can interact with me on my email. You can send me email on Priti, PRITI @sail.in, SAIL.in. Thank you.
Anyone have any questions? Okay, thank you so
Aini
much,
ma'am.
ma'am. Yes, sir.
Excuse me, Aini ma'am. We received a question through chat. Difference between carbon goals and carbon metal. Can you convert carbon gas to carbon metal or carbon fiber?
This is a question which I am not competent enough to answer. I think you will have to, but I can try to find out your answer if you send the mail. Uh,
Sure, ma'am.
Ah.
Wait.
Thank you.
Thank you so much, ma'am, for such a motivating and insightful speech. Your speech and idea have truly inspired us and reminded us of the power of determination and innovation. Your words have given us new insights and motivation to think differently and act with the purpose. The experience and ideas you shared will surely leave a lasting impression on all of us. On behalf of everyone present here, I express our heartfelt gratitude for taking the time to be with us today and for enlightening us with your valuable thoughts. We are deeply grateful for your presence and for sharing your valuable time and wisdom with us today. Thank you once again, madam. Now, today we will take a group photo. So, I am requesting everyone to keep on your video at that time.
Participants, please, for uh, to get a moment together, we are requesting you all, please put on your videos so that we can take and we can capture the moment.
वीडियो में
Last moment, please put on your videos. I'm taking every glimpse of our collective movement. Thank you very much for cooperating. Some of you hadn't even put on their videos. I'm requesting you all that we are collecting the snaps of this get together and this very much delightful experience of ours. If you kindly put on your videos, we can collect the skins and we will send it to your WhatsApp group. I had collected those who had already. Jobil Varghese sir, please turn your skin. Your face is in. Thank you, sir. Thank you very much, sir. Thank you very much, sir. Shobhik sir, Dr. Chandan Raj, Nitish Kumar Prajapati, Vikas Mandal, Samir Sharma sir, Sanat Kumar, Rajiv Ranjan, Dr. Tashaul Sheikh, Dr. Abhishek Sinha Mahapatra, Ankit Kumar. Please put on your videos if you can. Aniket Jadhav sir, Asim Kumar Mahato sir, Ravikant Prasad sir, Divya ma'am, Shobhik sir, Rajiv Ranjan sir, Dr. Tashaul Sheikh, Dr. Abhishek Sinha Mahapatra, Ankit Kumar sir, Dr. Abhijit Kundu, Arnav Ghosh sir, Arif Raja sir, Ratnesh Kumar Mahato sir, Sanita Chel De ma'am, Dr. Syed Ibrahim Baje sir, Kartikeyan K sir, Pranab Kumar Bande sir, Mohammad Abid Hussain sir, Dr. Arindam Goa sir. We have some photos. Lots of you hadn't put on your videos, so we couldn't collect the snaps together. And we will surely send it to the WhatsApp group, Dr. Shamesh Sharma sir. Okay, so thank you very much for giving us this opportunity to take the pictures. And our next session will start now.
Good evening to everyone present here. I am Komal Kumari, Assistant Professor at Ramgarh Engineering College, and it's my pleasure to welcome you all once again to this faculty development program on the topic Carbon Capture and Storage, Advances and Applications, to be delivered by Dr. Amrit Mukherjee, sir. It's a privilege to address this distinguished gathering on a subject that stands at the forefront of global climate discourse, carbon capture and storage, widely referred to as CCS. As the world accelerates its transition towards sustainable and climate resilient solutions, CCS has emerged as a highly promising and technologically sophisticated strategy capable of substantially reducing industrial carbon emissions. The rapid rise in atmospheric CO2 level is one of the biggest contributors to global warming. Industries such as cement, steel, power generation, fertilizers, petrochemicals, and refineries are major sources of these emissions, while renewable energy is growing rapidly. There are several industrial processes where emissions cannot be avoided. For such sectors, CCS is not just an option, it's a necessity. Experts estimate that CCS could contribute up to 20% of global CO2 reductions required by 2050 to meet international climate goals. It is therefore an essential component of the global strategy to achieve net zero. CCS is not a competing technology to renewable energy. It is a complementary and essential pillar of global climate action. As we move toward a sustainable future, CCS provide us with a powerful tool to decarbonize hard-to-abate sectors, develop new technologies, and build climate resilience. Now, it gives me an immense pleasure to extend a warm and heartfelt welcome to our distinguished expert for today's session, Dr. Amrit Mukherjee, sir, who is an assistant professor in the Department of Computer Science at the University of South Bohemia, Czech Republic. Sir, we are truly honored to have you with us today. With his years of rich academic and research experience, Dr. Mukherjee has established himself as an emerging scholar in the field of computer science, contributing significantly to advanced research, high-quality publications, and international collaborations. His work in Europe's prominent scientific and academic ecosystem reflects a combination of strong foundational expertise and innovative thinking. Dr. Mukherjee's association with the University of South Bohemia, one of the well-organized institutions in the Czech Republic, has provided him with opportunities to engage in interdisciplinary research, cutting-edge computational studies, and global academic partnerships. His contributions extend to teaching, mentoring, and guiding students across diverse domains of modern computer science. Today, as we come together for this faculty development program, we are fortunate to have him share his international perspectives, research insights, and emerging trends in the field. His presence not only enriches the academic value of this FDP, but also inspires all of us to strengthen global academic collaboration, innovation-driven learning, and research excellence. On behalf of the organizing committee, faculty members, and all participants of this FDP, I extend a very warm welcome to you, sir. We deeply appreciate your time and your willingness to connect with us and share your valuable knowledge. We look forward to an engaging, informative, and thought-provoking session ahead. Now, I would request Amrit sir to proceed into today's session. Thank you, sir.
Thank you very much. Am I audible? Please confirm.
Yes, sir, you're audible, sir. Yeah.
Thank you so much. Okay. Well, before starting this, I think, first, let me introduce myself. As already told, my name is Dr. Amrit Mukherjee, and right now I'm working here in Czech Republic since last 3.5 years as a senior assistant professor in research. So my area of expertise is a bit interesting for this topic because today's topic where I need to speak about CCS and its advances and applications. So my topic is a bit twisted towards the wireless communication and AI, IoT, smart cities. So when I got this topic, I profound like this could be a something new, adventurous for the whole audience, for the FDP part, because when we heard about carbon capture and storage, so mostly the expertises, let's say the first thing which will come to your mind is all about the carbon part, all about the some chemical mysteries and all. But let me with my slides, with my whatever expertise I'm having, because my area of interest, as I've told you, is wireless communications and AI, cognitive radio. So I will try to move down the same topic from CCS to the applications. Let's see, I can say the digitization of CCS, from where it started,
Sir,
like the phenomenon.
sir,
Yeah.
sir, can you put it in the full screen mode?
Sorry. No, actually, I've not started yet. Yeah, yeah,
Okay,
sure,
okay,
sure.
sir. Okay, sir. Thank you,
Yeah,
sir.
yeah. Thank you, thank you, thank you. Yeah, so so the flow will be first we'll start with the CCS and then we'll move to it. Okay, for this part, I will turn off my video and the full screen mode. Yeah, yeah. Well, so let me carbon capture and storage where excuse me, where we can see like in general, I think you have already attended some of the FDPs, so the basics are always the carbon capture and storage, CCS. Let's say CCS is a process which is designed to capture carbon dioxide emissions. Nowadays, everything, the world is moving towards green globe, and there are so many climate changes, things are going on. So carbon capture emissions from the use of fossil fuels in electricity generation and industrial processes, these part are very important for us. As I assume, like most of the audience, they are from the academic, they are from the research part, research domain. So somewhere, somewhat, let it be some embedded system expertise, wireless communication expertise, or some other microcontroller, microprocessor, antenna expertise. So at the end of the day, we try to somewhere I feel we try to focus directly or indirectly the reduction, or let's say we can say in terms of CCS, the process with capturing the CO2 part indirectly or directly from point sources such as power plants, industrial facilities where fossil fuels are burned. So if we are an expert in the sensor networks, if we are an expert in the microwave controller or some antenna designing, or let's say we are an expert of AI, so somewhere our goal, somewhere it goes deep down the stream into how to reduce it. Okay, so at the end of the day, if you see the carbon capture and storage, CCS is completely a phenomenon which has been introduced to decarbonization of whatever technology we are having. In terms of it can be of any example, let's say for steel production, cement manufacturing, chemical process, and so and so. So somewhere it is affecting the global temperature. And at the very beginning, we are the researchers. We want to publish the paper. We want to do our PhD, and we want to complete the things. And finally, when we become somewhere related with the academicians, so of course we need to perform our goal. But yes, the energy efficiency, the energy consumption, the energy storage, or let's say the zero emission goals, as I've highlighted in this particular point, is somewhere directly or indirectly connected with our topic of interest. So that's where the carbon capture technologies, or the new technologies that have been developed by different researchers, that comes into play. Now, in my uh, in my forthcoming slides, or in my overall lecture, I will be focusing on three different technologies. The first one is cognitive radio technology. Of course, it is a purely wireless network based, wireless communication based network. I am expertise in that, but I have tried to connect the same technology into CCS. The second will be our blockchain, and the third will be our quantum computing. Now, let's moving to the next slides. Let's have it quite a brief about this. Like as you can see, there are four main types of carbon capture methods: post-combustion, pre-combustion, oxy-fuel, and direct capture. Now, in case of post-combustion capture, which is nowadays it's most developed technology, even Tesla, they have set up some new different industries in New York, especially for post-combustion capture. Still, they need some government permission on that. So, still, the things are going on progress well in USA. So, basically, it involves extracting CO2 from exhaust gases after fossil fuels are burned. And the best part is like somewhere it can be retrofitted into the existing plants. Yes, there are some challenges, of course, like it requires a bit considerable energy to separate CO2 from other gases, nitrogen and all. But yeah, the challenges will always be there. But still, in the post-combustion capture, the works are going on quite smoothly nowadays in the market. Coming to the next one, that is pre-combustion removal after removal after burning. Like generally, it converts the fuel into mixture of carbon monoxide and hydrogen gases, and finally, the carbon monoxide. Then there are a lot of sources of carbon monoxide, and it has been further processed with CO2, hydrogen, CO2, kind of oxychemical things. The next is oxy-fuel combustion. So I'll not go much into details in this chemistry part. Like generally, as we know by the definition, it captures the CO2 by burning fuel in nearly pure oxygen, and with minimal nitrogen present, the resulting exhaust is mainly CO2 and some of the water vapor and all. So basically, effective method will be like just for the oxygen production, but still the challenge is the overall process takes a lot of energy. A lot of energy, that means whatever you are doing it, we are doing it to reduce the number of to reduce the carbon emission. But at the end of the day, the energy consumption overall, it somewhere it motivates or it dominates the carbon emission part. So somewhere we are playing in the negative. And finally, there is one more thing. Theoretically, direct air capture, on the other hand, let's say CO2 directly from the ambient air, although energy intensive, still these things are in early stage. But yes, it always helps to reduces the part of CO2 emissions. Now, somewhere when we move towards with this present situations, the AI and machine learning, these things are being integrated in all of the above four different technologies. So somewhere AI and machine learning, they plays a vital role in doing the processing part. Let it be the chemical engineering part, let it be the electronics part, let it be some microcontroller embedded sensor network part. So somewhere AI and machine learning is been one of the very important factor that comes into play already in last 3 to 4 years. But still there are the challenges remains. For example, scaling this technology to meet the global emission reduction, which is quite expensive and it's not sustainable yet. So somewhere we have to focus on the sustainable part as well. Moving to the next one, that is monitoring and automation of CCS. So here, once the carbon dioxide is captured and injected, so somewhere continuous monitoring and safety assurance is one of the very primary factor, or let's say is the foremost important factor that comes into play wherever the technology is being implemented. Let it be in the public platform, let it be in the private platform. So there are some public regulators, operators that ensure that whatever carbon dioxide is being produced is not leaked back into the atmosphere, which will definitely create some environmental negative impacts. So to monitor them, to monitor the safety of this, there are various system being implemented. Nowadays, they use optical sensors which are embedded in different walls in the pipelines where, as you can see, like in different companies, different industries, there are big chimneys. So there they are trying to fit different variety of sensors which will identify and monitor the same thing, the same whether there are some leakage or not, or whatever the amount, whether it is exceeding or not. So in this way, it works. Now, as I told you in the last slide, AI and machine learning algorithms are very much important for in today's constraints, where these machine learnings and AI helps that particular sensor that have been fitted in the pipeline. They help us to analyze the large volume of data collected from from the emission happening. And somewhere those who are quite familiar with the term called edge computation, edge computations, edge communications. So for them, it will be easy to analyze, like these type of sensors. They try to collect the same emission from the carbon dioxide from different pipelines and all. And finally, they try to analyze the very basic things, the basic calculations, the basic communications among each other in such a way that they will form a group, and the group will, the information from the group will move to the cloud. So if you can see, the flow is, we are trying to move the same thing, the same concept of CCS from the analog part to the digital part. Okay. Now, so here you can see the role. This part is quite clear. For initially, we are trying to optimize and capture the process, then revolutionize material design, improve site selection, where AI plays a vital role. As I've already told you in the last slide, the AI, the sensors, those who are connected with each other, for specifically different gas sensors, methane sensors, carbon dioxide sensors, carbon monoxide sensors, and so and so. And finally, with their output, as like in case of edge detection, the fourth point works that is the real-time anomaly detection. So in this particular case, the real-time anomaly detection, wherever they find something abnormal or some anomaly in that particular results of the carbon emission from that particular industry. So that time they try to figure it out, what is going on or what is happening, or they try to warn. So based on our programming with the AI or some AI, there you can use different algorithms, particularly which can analyze the real-time sensor data, or let's say historical performance records, which dynamically adjust their operational parameter according to the situations, basically according to the applications and situations. So for instance, when capturing CO2 from some random gas, flue gas or something, the AI model which has been implemented, they can recommend, for example, the ideal solvent flow of the temperature, or how to improve the efficiency, or whether we are using some extra sensor, like just that will cost a lot of money and a lot of as well as energy, that will consume a lot of energy. So somewhere they will try to modify the circumstances based on different various different factors in case of CCS. And finally, at the end of the day, to integrate into control systems, where we are trying to put all the effective outcomes of all the sensors, of all the let's say all the parameters that have been monitored with the analog sensors, digital sensors, different meters, systems, subsystems. So we'll try to integrate it, because our aim is just to implement AI in a very much ethical way, very much sophisticated way, and that's it. Well, this part will be of a bit interest to you, maybe. Now we'll try to move CCS towards my area of research, that is cognitive radio sensor network. So I will try my best to connect these both of these things, just to make sure like you are comfortable understanding one of the technologies which is available in the market, which is mainly somewhat around 5 to 6 years back. It was boom, the cognitive radio, and then later on there are some sensors that has been implemented in the cognitive radio phenomena, and the term called the cognitive radio sensor networks, which is I can say like which is one of the very few technologies which can be implemented in CCS, just to make it a smart CCS in a way like if I need to say, I can say like traditional sensor networks, they tend to operate on a fixed spectrum allocations, which is not the fundamental of the cognitive radio sensor networks, because those who are aware with the cognitive radio sensor networks, for them it will be easy to understand that cognitive radio is a phenomenon where someone is using unlicensed band in such a way that the licensed user is not getting hampered. Now, exactly the same phenomena when we put in within the sensor networks, and we will try to implement cognitive radio sensor network. Just we are doing the same thing when we'll try to implement the same set of sensors, which I've already explained you in the previous slides, and that is in different, let's say, in different pipelines for the liquid, or let's say for the flow of gases and all. So exactly we can do the same thing, but here the magic happens only because of the cognitive radio part phenomenon, where it only try to use the available spectrum which is not being used in the company for that particular instance, and they have their own intelligence. That's the best part about it. So because of that, the whatever sensors you are putting it physically or digitally inside that particular pipeline, where the liquid flows, where we want to reduce the carbon emission, CO2, different gases, different chemicals, and so and so, or in the pipeline, we are trying to do exactly the same within cognitive radio sensor networks. And these sensors, they have their own intelligence. So because they have their own intelligence, it's very easy to focus on this particular 3 points, that is distributed flexible network for leak monitoring and infrastructure health, efficient management of massive sensor data streams. Now, this is what I was talking about, the effective management of massive sensor data streams, where there are a lot number of, it's like you can say easily it's more than 100 or more than 500 if the industry size is quite big, or the industry emissions are quite big. So of course, the number of sensors, they are having their own intelligence, and they are able to perform their own spectrum analysis, spectrum management part without the help of any external thing. Of course, if the question arises, can we infuse AI with with cognitive radio sensor network? The answer is yes. Yes, we can do the AI with cognitive radio sensor networks, but yeah, there are so many theoretical papers available online. But in practice, me and my team, my postdoc and my PhD team, we are working in this particular field, but till now we are still struggling, because to infuse AI in a sensor node, it seems quite a hard bit of job. But still we are trying. So somewhere, let's see how it works. Yeah, but theoretically, yes, it's possible. Now, basically, if you see like the smart monitoring of CCS using CRSNs, they are the cognitive radio sensor networks. So you can easily see like, I can give an example. Imagine an industrial scale of which is having some CCS facility, where vast volume of carbon dioxide, carbon monoxide, and some various gases, they have been captured, transported, they have been transported underground. So these type of things, somewhere like for the safety and regulatory compliances, there will always be an issue. Now, to achieve these things, CRSN can work as a perfect solution. How? These networks, these particularly these CRN networks, those which will have some intelligent sensors that are capable of, as I told you, they have their own intelligence and they are capable of real-time communications and all. So they don't work like a traditional sensor networks, which uses only some certain frequency bands, some standard frequency bands. Now that is the beauty about CRSN, which can be used in CCN, which can be used in CCS for various industrial applications, especially for their this for pollution monitoring or pollution like the level of pollution or different parameters that are involved in CCS. In practice, these technologies, this will help us to track the real-time carbon dioxide, carbon monoxide, and various other parameters involved in CCS, which will be somewhere which can be processed. I think I've showed you in the second or third layer, which can be pre-processed or post-processed based on the output of cognitive radio sensor networks. Well, there are some AI models that are available. Theoretically, yes, these things are available. In practice, I think Tata group of companies, they have introduced these things for CCS. I have read somewhere, and some of the AI models which I noticed in various papers, they are like adaptive sensor calibrations from anomaly detection, predictive modeling, and basic data analysis. So this part I have already told you about the anomaly detection part, and the rest are adaptive sensor calibration. So here, if you are if you understand the concepts of the CRSN, that is cognitive radio sensor network, so it will be quite easy to understand how the sensor should be calibrated in such a way that whatever network they are being formed, whatever network they are forming inside or outside, before or after processing of these particular carbon emissions. So AI will play a vital role because they have the existing data sets, they have their test data, train data, everything. So yes, those from the audience, those who are quite comfortable in AI, they know various techniques, CCN, DNN, and all. So yes, these techniques can be implemented in various sensors just to pass on the threshold, or to study the threshold, or to study the limits of each and every sensors, as well as for a cluster of sensors, as well as for the inter-cluster and intra-cluster sensor networks. So all these things are related to the CCS. So at the end of the day, being a researcher or being an academician, if you are not directly related with the CCS particular part, so yes, we can digitally focus our research or our aim of the studies, or to design some projects based on this particular CCS. Okay, moving to the next slide, that is integration challenges. So here, as we know, like the digitization and automation of CCS systems, they used advanced sensor networks like CRSNs and AI. So these somewhere it confronts the significant integration challenges, because when we it's very easy to say just to implement AI with the sensor networks, but in physical we know it's very hard. It's very hard to implement, and especially when we are dealing with the ad hoc based sensor networks. So yes, there are some integration challenges. This is one of the challenges. When of course, at the back of the coin, the other side of the coin is always there are opportunities. So these opportunities will help us, being a researcher, being an academician, to go for various wireless communication, or those who are expert in CCS, so they can go for physical environment, especially for different CCS operations and all. So The challenges may also include high pressure, humidity, underground settings where the sensors they can attenuate, distort, because in the underground the conditions are completely different, not like the air, where we can implement directly the mathematical modeling of AWGN relay feeding channel. So everything changes. So because these are some of the opportunities as well as the challenges, so the researchers are nowadays they are trying to make their object, their study in such a way that everything should be energy efficient, which is directly proportional to the CCS theme. Now, moving to the next slide. Beyond CCS broader environmental applications. So here, here I would like to discuss about the CRSN specifically, because the CRSN and AI-driven smart sensing technologies, these are the future technologies which will directly impact CCS. And somewhere nowadays in let's say an example for urban air quality monitoring, I think in New Delhi there is some monument or some kind of statue which monitors the air quality and try to purify it. I just saw it in news. So that kind of in that kind of particular real-time scenarios, the implementation scenarios, CRSN will play a vital role to work towards CCS theme. So here you can say these things are important for large pollution level. Network sensors are deployed to detect concentrations of particular matter, nitrogen oxide, ozone. CO2 is quite obvious, carbon monoxide, some various harmful pollutants, and so on. So the beauty of using CRSN in this particular part is like because cognitive radio sensor networks, this allows sensor networks to operate reliably in dense urban environments, and that is the best part. Like the whole setup, the whole ad hoc network setup of CRSN, it can be implemented underground as well as above the ground and in any places. So these are some of the benefits of using CRSN. Cognitive radio and AI for net zero initiative. Well, net zero initiative is quite similar to zero emission waste. So here, the cognitive radio sensor networks, they represent a big jump in the in developing environmental monitoring. So those who are quite familiar with this particular term, smart environment, so specifically it's for them, like the conventional wireless sensor platforms in hardwares. The CRSN hardwares, where it try to dynamically assess and use the available spectrum, minimize coverage. The overall system is quite reliable, quite sustainable, and the best thing about this is like we can implement these technologies in an unpredictable environment where there are a lot of noise, where the air quality changes continuously, or you are there are some research papers where they have tried to implement AI with CRSN for CCS specifically for underwater applications. CRSN was quite impressive. Now, these are basically, when I'm talking about the AI, so these are basically paired with AI networks just to make the overall process, like whatever the data the sensors are capturing, the AI is helping the sensors to finalize the decision, or the cloud or the internet. So wherever you will try to implement the AI, if we are trying to implement the AI in edge, that will consume a lot of energy. And since there in the wireless sensor networks, as I'm talking about, as we know, the wireless sensor networks, they operate with a very small batteries. So if we need to implement the AI in that particular small battery-based sensor, so definitely it will consume a lot of energy. So somewhere that is still a challenge, which the scientists are working on. So, but yes, with the help of AI, whatever the data are been collected by various sensors in inter-network, intra-network communication and computation. So the AI is helping them to classify or to organize or to go towards the net zero initiative, where the energy consumption should be as low as possible, or the overall monitoring should the accuracy of the monitoring should be as high as possible. So this is the goal. Well, in the upcoming slides, I was having a research paper, so I will try to connect the same thing, connect my same research paper with the CCS fundamentals, and that is cognitive radio sensor networks for visually impaired individual for smart healthcare applications. So here I won't I'll not go much into the technical part, basically the fundamentals of doing this or the implementing the cognitive radio sensor networks was for the visually impaired individuals, those who are working with some sticks or some particular devices or their wheelchairs. So they are able to diagnose or analyze using AI with the help of cognitive radio sensor network. So that was a plan behind it. So somewhere, if you ask me like how to relate this particular topic, this particular theme into CCS, so I would definitely tell you, like, if that visually impaired individual, if they're using some traditional methods of sensors or some other embedded system devices, so yes, they have they have various problems which will include more and more battery consumption. So because it's more and more battery consumptions, your battery is related to the power. The power is related with the carbon capture storage. So somewhere cognitive radio networks has been quite successful in implementing them. This is a diagram just to show and how it's working. So I'll directly go to this particular part. Yeah, the algorithm which I have tried to implement was there were two algorithms, which is the first one is to initialize cognitive radio sensor networks, to deploy the sensors in the environments, and how it is working and what are their observations. So we are trying to collect it. And the second algorithm is exactly doing the same thing while using AI. So they are trying to do the same thing, almost the same thing, in such a way that the data collection should be as maximum as possible, the energy consumption should be as low as possible, and to perform the same act. So mathematical formulation. Some of the output where we have tried to show that the curve, they are quite when we are using some various neural networks, so our output were quite satisfied as compared with the traditional. So here I have not explained the traditional, but yeah, the overall edge networks were performing the performance where we have taken the real-time data and we have tried to compare it, and the result were quite satisfactory. And this paper, the first draft of the paper has been published in IEEE conference, and then we extended the same thing and we published it in IEEE transactions. Some more results with advanced PSO and copula methods. Well, okay, so here I close my first topic, and that is the CRSN part. So after this, as I've told you, let us move to the next interesting thing, that is the blockchain, and how in this particular lecture I told you I'll be discussing about the cognitive radio sensor networks, then blockchain, and then finally the quantum computers. Quantum computing. So finally, we are moving towards the next topic, and that is the role of blockchain in environmental technology. So here, those who are quite familiar with the blockchain and those who are they don't have idea. So let me start with a very basic thing. Like blockchain is generally you will hear this particular term in terms of cryptocurrencies, where the decentralized ledger, transparency, immutability, and all these things they happens. So generally the blockchain they work in terms of different various connectivity where the connections and the mining, they are quite related with the highly developed quantum computation. So the overall aim of this particular of introduction of this particular digital technology which will connect CCS is to give you a basic idea like how the blockchain will be affecting the CCS part. Well, okay, yeah, this is quite interesting. Blockchain in CCS data management. So in terms of CCS, let's say the blockchain is always valuable for logging, tracking, verifying the full chain of carbon dioxide, CO2. So as we know, the blockchain, they consist of a large number of n number of unknown chains. So here, if we consider the application of CO2, yes, they can help us for tracking and verifying the full chain of carbon dioxide handling. So the companies, those who are handling the companies, the step by step how it started and how it's getting emitted and what are the different levels and how the captures. So everything can be like everything as a researcher we can form it in terms of blockchain. Of course, if we are doing the same thing, so that will definitely help us for initial capture, for transport, or for underground storage, and so and so. So yes, the blockchain plays a vital role. So here, there are, as you can see, there are some pros and cons, but let me start with the very basic facility. So for example, at every point where the carbon dioxide has been separated from various industries and all, with with compressed and transported via pipelines. So here, uh, if the data is getting manipulated, let's assume such a case like if the data is getting manipulated, or if the data is getting lost, or like someone working in the company, so by mistakenly he has typed some incorrect log, or which will indirectly or directly it will hamper the blockchain, and finally that is directly proportional to the CCS part and the credibility of the operation. So that has not been expected. So the nature of the blockchain, the theory of the blockchain is blockchain's decentralized ledger allows each data point for every transfer, or let's say for every transaction, to be recorded in a tamper-proof way. To be completely recorded in a completely tamper-proof way, so that if there are any, by mistake, if anything happens, the data lost or someone stole the data or something happened, so with the help of blockchain, the data will be saved. Well, this particular transparency is having an immediate impact on the stakeholders' trust. Though the stakeholder means those who are having some shares on that particular investment. Let's say it may be some industry, some smart industry for which like those industry, those who are those who are implementing industry 4 or industry 5 kind of thing. So somewhere CCS is related, and moreover, if you can say, the blockchain facilitates environmental compliance. So if we go for the environmental rules and regulations, so yes, the blockchain follows them. So whatever happens, let it be with the in expense of the high initial cost, or applying like the scalability issues. So these are the cons. Of course, these are the some problems associated with implementation of blockchain. But at the end of the day, if we are quite satisfied with the pros, so I think the industry 4, industry 5 should move towards the blockchain part in developing, like in association for the CCS. Well, this is a very important topic, and I hope like this is a very common word like carbon credit. So this is somewhere the climate action and the digital technology, they when they interact with each other, so the word carbon credits comes into play. So here, what is the role of blockchain? So the blockchain based carbon credit platforms, the platform, those who have been developed by different blockchain developers, so they know like, yes, our platform is quite carbon credit platform, so we can be trusted, so the industry can trust us for their transparent, for their audible trading, for their emission reduction. So these kind of credits, these kind of points, the developer, they try to develop in such a way that every credit which has been issued is recorded in every transaction. So the way the blockchain, the blockchain plays, the blockchain works. So in every transactions, the credit has been noted, the existing credit, the present credit to that particular node. So in this way, every node is getting updated every time. So there is no, like, there is no fear of information loss, no fear of delivering some wrong results or wrong timing, because every node is getting reactivated and re-updated every time. So this is where the carbon credits comes into the play. So more the credits, more the dependence, more more the trust. Now, moving to the next slide. Here comes the cybersecurity challenges in CCS digital ecosystem. Well, as we advance towards the CCS system, it is very crucial to recognize that whatever digital process that comes new, for example, I've told you about the CRSN and all. So there are some risks, or there are always some risks about the cybersecurity part. This is directly or indirectly will hamper the CCS performance. So this, I'll give you an example. Let us consider a shift, that is a shift in the digital industry requirement. So the modern CCS operation will try to try to analyze the data, try to gather the data, try to perform and try to spread whatever are the social impacts, whatever are the different economical impacts. So all this information, somewhere, somewhat, there may be some cyber attack. Who knows? So in case of that, that remains, there are some possible solutions. For example, we can always use some computation based algorithms for this kind of cyber attacker. But yes, again, anyone can challenge. Yes, they are also smart. They can also use quantum computations things. So yes, there are some quantum games that is going on with the cyber attackers and the security personals. But at the very same time, we have to see like there are some advancement in the quantum computations as well. We call it as post-quantum computations, PQC. So yes, they are in the another advanced level. But again, if we try to implement the same thing in blockchain, so that will create a very much complicated situation. Yes, that is theoretically possible, but practically when we want to implement them, so it will consume a lot of energy. This energy has been consumed by the server, who is the server and the servers, multiple servers, those who are performing the blockchain part. So yes, these are the benefits as well as these are the challenges. Moving to the third phase of our topic, that is quantum computing. So I'll be discussing about the post-quantum computing part. So this part, how it is related is like, I can say this particular part, the fundamentals of security of cryptographic system. There are various RSA, ECC and all. So these all comes under the quantum computing, as we all know, and they are also used in various online banking, blockchain transactions in terms of cryptocurrency, bitcoins and all, bitcoins, ethereums and all. So yes, they use quantum algorithm, but at the very same time, the CCS based sensor communication, they may get hampered or they may get affected. So there is no perfect solution for this for the timing right now. But yes, the researchers, they are working on this, because if anyone tries to hamper the quantum computing, the post-quantum algorithm, so they are somewhere, they are trying to go into the blockchain, which will create an immense earthquake in the blockchain, various nodes, various servers and all. So moving to the very basic of the post-quantum cryptography. So here, those who are quite familiar with this and those who are not, basically this post-quantum cryptography algorithms, they are basically lattice-based, hash-based algorithms and code-based algorithms. So these are the different technology they use for post-quantum cryptography, and nowadays the trend is going on how to hack a blockchain using post-quantum cryptography. So there are various hackers, and even they organized some of the different hacking competitions also. So they have some very interesting results, the winners, but they have not displayed them publicly, of course, due to the security issue. But yes, this is one of the very interesting phenomena for the post-quantum cryptographic basics, where they try to implement or they try to inject their expertise in the blockchain ledger, especially. So the challenges that they face in post-quantum cryptography are the larger key sizes, because they are trying to implement lattice-based, hash-based, and there are different researchers, different developers, those who are using both of them based on different locations or based on different type of information, and so due to that, of course, the challenges become larger key size. This particular larger key size will directly impact the energy consumption, which will directly impact the server energy consumption, the power consumption by the server, which is directly connected with the CCS part. Then comes the computational demand. So as we move toward the post-quantum cryptography, the computational demand also increases and it will never stop. So as the demand increases, the complexity increases and the time consumption increases, the energy consumption increases. So everything increases. But yes, the security also increases. And implementation complexity. Need for PQC in blockchain. So in this particular slide, as we know, the vulnerability of classical blockchain, I've already told you in the previous slide, there is an urgent need of PQC in blockchain system. So if we are trying to use blockchain, which is a distributed ledger technology, and we are trying to implement some technologies, for example, RSA or elliptic curve cryptography kind of thing. So there, the problem is to authenticate transactions, to protect the keys, and establish consensus mechanism, which is one of the very important part in blockchain. So these parts, if they are being able to implement in blockchain, so we need PQC. There are some benefits of PQC. Of course, there are some pros and there are some cons. The cons we have already studied. I've already told you in this particular slide. So here, if we go for the pros, so these are like, somewhere for various environmental applications, for various consumer electronics applications, for various vulnerable blockchains, and so here there is definitely a need of PQC in blockchain. Of course, this is directly interacted with the CCS, because if we are trying to modify, we are trying to make the PQC smart in such a way that the overall algorithm will consume very less memory and very highly efficient. So that can be easily implemented in the blockchain, which will consume less energy, which is our ultimate goal for CCS. Well, now integration PQC with CCS digital platform. So if you can see, like, one of the core technical challenges in deploying PQC directly to the CCS system. Let me tell you, till now it has not been done. There are some research papers, so based on that, I've collected the information. So if we try to implement the PQC in CCS system, which is let us assume it's sensor based or sensor network. So sensor networks in CCS, they often consist of n number of low power, low memory, low computation devices in various underground, outdoors, and so on and so. So if we try to implement PQC algorithm, which is to implement PQC algorithm, our sensor network should be able to handle that particular memory, that particular action, because as I've already told you, to fuse AI in a very small sensor, still it is a tough job. So if we are trying to implement the same thing, if you're trying to implement the PQC in digital platform, that also is somewhere it's a challenge. It's a challenging job, although it is very much important that we need to save, we need to protect the transmission confidentiality, authenticity, and integrity amidst all quantum risk. So as we know, as we have told that in the previous slide, in the blockchain era, the PQC is it is having pro as well as con. The pro is, like, if we try to implement PQC, it will be better, but at the very same time, the blockchain can be hacked using PQC. So somewhere it is a risk, but it is important. The next one is secure data sharing in CCS using blockchain and PQC. So I think most of the points already I've covered. The interesting part, the use of the blockchain and the PQC, individually I've told you, and if we try to combine all of this, integrating PQC or need for PQC, so this is a combined slide where we'll get a brief idea about, like, how the data is quite secured in CCS using blockchain and PQC. The blockchain, we already know, distributed ledger part, it works with the consensus. But at the very same time, when we talk about the PQC, so yes, it's quite challenging. We want to implement it in different sensor networks, and then to the blockchain or the different blockchain nodes, or maybe in the blockchain servers. So overall, if we do such a thing, then yes, the CCS can be the data will be secured and it will be quite sustainable as compared with the traditional methods. Quantum resilient CCS infrastructure. This is something different where where the CCS is been try to where we try to roadmap the vision of CCS ecosystem along with the quantum resilient infrastructure. So here, because it's a quantum resilient infrastructure and can be established in isolation, so cross-sector collaboration is very important. Sector collaborations means some engineers from mechanical engineering, someone from civil engineering, or a different let's say with a different biology background. So yes, they can come together and work for cross-sector collaborations using this quantum resilient infrastructure towards our CCS goals. Then IoT, Internet of Things for CCS data collection. So I think in the previous slide, I have already discussed about the cognitive radio sensor networks. So just try to assume the same thing, the same phenomena where various sensors, they are connected with each other and they are connected with the internet and they are having the AI. So exactly the same thing which IoT is doing. The difference between CRSN and IoT is CRSN may or may not be connected with the cloud or with the internet, while as IoT in general, in theory, we always assume that the IoT is connected with the internet part. Distributed data processing in AI in CCS. So here, when it comes to maximizing safety, now we are moving towards the safety, efficiency, responsiveness in CCS. So this part, this distributed data processing and AI plays a vital role. Specifically, as we have discussed about the sensor network, so these sensors, they have their edge nodes, which is capable of doing the local computation part. So each node, they try to aggregate, they try to collect some incoming sensor data. They run preliminary pre-processing, post-processing and all. And finally, if we deploy the AI models right at the source, then the edge will be a smart edge communication. So exactly that is how a distributed data processing and AI comes into the play. Next, blockchain for secure CCS data management. Well, here the blockchain offers a transformative solution because everything which we are learning today in this particular lecture. So these things are related with distributed tamper resistance. In short, the overall features of the blockchain. So yeah, there are some fundamentals of blockchain as well. If we go for proof of work, proof of stake, so directly or indirectly, if we are trying to move or our key parameter remains the same, that is carbon dioxide and various other different gases. So how to reduce them? So yes, the blockchain is one of the very great strength in CS, in CCS, specifically for the digital world. Well, smart contracts, there are various examples. For example, smart automation, smart data management, where there are some self-executing digital agreements coded, and so and so. So somewhere the CO2 injection is needed for safety threshold and contract. So if we try to compare, like yes, we are trying to implement the CRSN and everything is going smooth using blockchain, but your server is consuming some energy. The server is been operated by some hydrothermal power or some chemical power. So they are producing the energy where the server is working, and there are multiple multiple servers. So yeah, the CO2 is been hampered somewhere. Blockchain integration with CRSN and IoT. I think this already I've told you. Energy efficiency in cognitive radio sensor networks for CRSN. So here, if you try to implement the cognitive radio sensor networks, so there are various energy efficiency techniques. There are various energy efficient algorithms where multiple sensor nodes can form a cluster. They can communicate between each other in intercluster model, and as well as in the edge communication part, where the sensors, they have their own intelligence. So the overall fundamental thing which I need to speak is to consume as less energy as possible, which makes the overall system energy efficiency, specifically for CCS. There are some scalability challenges in CCS networks, as you can see, sensor density, coordination challenges, computational complexity, spectrum computation, wireless interference. So all these things are related with if I need to talk about the sensor density, if there are more sensors, that means there are more computational complexities. If yes, there may be some coordination challenges also. If one sensor is not working properly, then it may or it may not contact to contact another sensors, or it may provide some false information. So that may create some problem, as well as some wireless interference. Okay, some other challenges are bandwidth and data transmission, data aggregation, compression techniques. So all these are related with the wireless communication part, the wireless channel part. Then it comes to the computation part where we can say post-quantum cryptography. If we need to try to implement the post-quantum algorithms inside the sensor networks. Scalability limits the number of as the number of sensors increases, the range of the overall network increases, which is not good, I would say, and that may create sometimes the problem of the due to a large number of distance, due to a large number of interference as well. So, and blockchain and security, yes, of course, I've discussed this particular point. IoT sensor calibration and validation in CCS. So here, how accurate my sensors is working, how accurate my wireless sensors, the cognitive radio sensors, they are working. So if we need based on the CO2 input or some other gases input or some other chemicals input, so we can, yes, we need to calibrate it based on the requirements basically. And if at all there are some blockchains, so the blockchain will record the calibration logs for audit transparency. So the blockchain will record everything. And as we know that it's based on distributed ledger concept, so all the nodes will, all the sensor nodes will have all the information regarding this particular IoT calibration. AI-powered anomaly detection. So here, this particular slide, we can see that the anomaly detection, as we have discussed in the previous slides, that is completely related with the outcome of various cognitive radio sensor networks, let's say blockchain, let's say quantum cryptocurrency, PQC. So everything, so whatever information and wherever we are trying to implement the AI, if there is any anomaly detected, which would directly or indirectly affect CCS. So these are some of the names, for example, blockchain integration, continuous learning, collaborative sensing, sensing where there are multiple different wireless sensor networks. It might be possible that there are one of the network is cognitive radio sensor networks, the other network is some different wireless net. So they are communicating between each other, and they have issues with collaborative sensing. So yes, in that time you can find some anomaly detection. Machine learning, any fault in the machine learning part, and traditional analytics. Smart contracts for automated CCS operation, I think, yeah, most of them are already discussed. Integration of cloud and edge computing in CCS. So about the edge computing, I've already discussed with you, and that is wherever we are trying to implement some edge sensors. So they are developing their, we are trying to feed some AI within it in such a way that the edge is able to do its own stuff, basically, to process the, to do the local data processing part. Now, in terms of cloud computing, when we try to fuse AI or in terms of CCS, how it is related, anyone can say like it requires the basic network connectivity, which is quite obvious, massive data storage in cloud, which is directly connected to the CCS, slower response time. Now this slower response time is due to the massive data storage, as well as in this particular slide, yeah, as well as due to bandwidth and data transmission. And finally, the centralized data processing part. Resilience and fault tolerance in CRSN for CCS. So, well, when we need to do something, we face challenges, but at the end of the day, we have to do it because we are the scientists and we have our own motivation. So the resilience and fault tolerance comes into the play. So exactly the same thing lies with the CRSN as well. So here, if we are going for the blockchain part, if we are going for different PQC parts, so we are trying our best to implement the technologies in CRSN as much as possible. So that the fault, the overall network should be robust, the energy consumption should be as low as possible, the computation complexity should be as low as possible, the computation speed should be as more as possible, and so. Now, there are some cross-disciplinary collaboration in CCS digitalization. So as I've already told you, like this is a topic which is of interest for various different categories for environmental scientists, process engineers. In terms of knowledge, those who are trying to invest their time in CCS, in the digital part of the CCS, they can go for cryptographic protocols, designing of them, analyzing of them, implementation of them, machine learning, various machine learning models, blockchain. Then collaborative tool development where they can use PQC as well as IoT. So, well, both of these technologies are completely different. But if you are trying to fuse it for the CCS digitalization, so yes, that is very much possible, and that will somewhere help the industry, industry 4, industry 5, and so and so, and even in various telecom industries also. And finally, the funding and regulations, which is sometimes which is within our hands, and sometimes we depends on various funding agencies for projects and all. Now, blockchain governance model for CCS ecosystem. So this is just a governance model where balancing speed and trust in blockchain, how to make them. Like there will be some issues, there are some issues there, but if we need to implement them, then in order to do that, we need to ensure the accountability and transparency, aligning governance with regulatory and legal frameworks. So these are some of the admin work which we need to discuss with various societies, or if we are trying to develop the same in the university. First, we have to check with the university norms, then we have to check with the local municipal norms, then government norms, and so. Future technologies that will enhance CCS. I have already told you about that quantum PQC. Even PQC is one of the future technologies. I've discussed it. Quantum sensing, advanced blockchain solutions, some AI-based algorithm for CO2, plum migration, integration of CRSN, which is already ongoing part. Synergies between PQC and emerging cryptography protocols, just trying to collaborate different various new technologies. And finally, the impact on CCS operational efficiency and environmental safety. This part is the end, but still it is the most important part, the most important motivation where a researcher should start working towards the CCS part. Here comes some socio-economic implications of digitized CCS. So some of the implications are real-time data streamlining, transparent monitoring, carbon credit system, which I have already explained you. So this carbon credit plays a vital role. Collection of more and more credits means the system is working more efficiently. So of course, there are some issues with denominations, because in different research papers, some of the research papers, they claim more carbon credit implies more carbon emission, which is like, in my particular opinion, I will be neutral, because there are some papers which will say the vice versa. So somewhere the carbon credit count, it matters, and whatever the PQC, the blockchain system has been developed, so it depends on it. Then predictive maintenance, optimized control. Now here, predictive in terms of predictive maintenance, you can always fuse the anomaly detection part and incentive adoption and ensure safeguards. Designing user-friendly interfaces for CCS systems. So this is just the same which I already explained you. I will go directly to the environmental impact and sustainability metrics enabled by digital CCS. So here, how the CCS can be implemented digitally, and trying to calculate the credible carbon credit training. So there may be some multiple businesses which are connected with each other, and they will try to calculate each other's carbon credit before they do some they do some their own businesses, or maybe some collaboration work with the municipality, or maybe with the government. So this is how digitally it has been done. Finally, the conclusion secure intelligence is the future, and that's the overall brief of what we have discussed till now. That is CRSN, how it is connected with CCS, blockchain, how it is connected, and PQC. And overall, if you see this will be a very common term which we have seen with CRSN, with blockchain, and with PQC. So the overall conclusion of my